The second speaker for this session is Alex Weeks from the University of Saskatchewan, and he will speak on Coulomb branches for Quiver gauge theories with symmetrizers.
Thank you for the introduction, and I'd like to thank the organizers for inviting me to speak. It's wonderful to give a talk, and thank you all for coming, whatever time it is where you are. Yeah, it's been a pleasure to see so many wonderful talks throughout this conference, and I have the benefit of being able to reference some of them. My talk will be about, as it says, Coulomb branches for Quiver gauge theories with symmetrizers, which more simply put just means, for quivers where you have non-symmetric types like type B, type C, type D, as we'll talk about. And I'll be using the language of algebraic geometry, much like Professor Nakajima's lectures this week. But I will try to make connections to physics as much as I can, or am able to, I guess I should say, and especially to content that's appeared in some of the lectures so far. So without further ado, sort of a summary slide. And I must apologize in advance for my handwriting. I recently got a new pen tablet, and I've been trying to hone my skills with it. But if there's anything that's unclear that's written, please don't feel free to interrupt and ask me. Yes, so I'm talking about 3D n equals 4 theories, which have been a recurring topic in this workshop. And I think it's hopefully clear at this point of the workshop how important and rich those are from a physical and mathematical perspective. And one of the ones that's most significant are what are called quiver gauge theories, which we have also seen several times. So I'll do a quick overview of them at the beginning of this talk after the introduction. But just for to remind you, what are we starting with? Some sort of picture like this. I haven't chosen any sort of orientations because that doesn't really matter. And when I have a picture like this, I want to think of this as associated to the Lie type A4 because there's this underlying Venn diagram here. And associated to this data, there is some 3D n equals to 4 gauge theory, whose gauge groups are determined by the circles, and the matter content is determined by the arrows. This is a very rich setting because on the one hand, this Coulomb branches associated to this setup have to do with geometric representation theory, as does the Higgs branch. But on the Coulomb side, we're seeing Affine-Grassmannians, or more precisely, Affine-Grassmannian slices. And we're seeing connections to representation theory through geometric satake. And maybe it's worth saying, this is at least for finite ADE types. Although I believe Professor Nakajima will be telling us about geometric satake in affine type A. And of course, it's sort of expected in general. On the other side of this picture, though, there's another beautiful story of Higgs branches, which are what are called Nakajima Quiver varieties, which are also very closely related to representation theory. This was talked about a bit by Professor Nakajima in his lecture today, a certain way of constructing a representation. So let me think of this sort of quiver gauge theory setting as a very promising setup for geometric representation theory for symmetric Kac-Moody types. And again, I'll emphasize this word symmetric because this kind of input data doesn't remember exactly the same thing as like a Cartan matrix. Namely, we can only have Cartan matrices which are symmetric. They're equal to their transpose. All that we're seeing is kind of a graph. There's no extra data here. And so a kind of natural question is, how do you extend this to allow more general diagrams? So, a more natural thing would be something like this down here at the bottom. Here, the underlying diagram, it's the same data, by the way, but the underlying diagram is type F4. So I've included this sort of double edge, whatever this means. Can we make sense of this as some sort of gauge theory? And well, short answer, I don't know personally. Can we build a Coulomb branch and a Higgs branch? Well, I'm going to answer, I hope, sort of one of those questions and talk about the Coulomb side. I actually don't know anything about the Higgs side in general, so it's a little bit mysterious what exactly we mean physically. But there is perhaps a well-defined Coulomb branch associated to this data. That's what I'd like to talk about. And I think that it's safe to say that there are sort of physical expectations for this as well. I'm thinking especially of the work of Hanani. He was talking about this also in his lectures. These sorts of graphs naturally would show up. And but from a mathematical perspective, what I'm going to talk about is some joint work with Nakajima, where we give a mathematical construction of a Coulomb branch associated to a input data of this type. And in a more technical term, it'd be a symmetrizable type. So there's some symmetrizable Cartan matrix that's supposed to underlie this. Of course, in type F4, that is an example of such a thing. And so we give such a construction. And second thing we do is we, in finite type, so B, C, F, and G, we showed that this construction recovers parts of the Affine-Grassmannian, or more precisely, what are called generalized Affine-Grassmannian slices. So this is to say that it's looking about right, at least from a math point of view. So the plan for this talk is to do, I guess, three things you could say. The first is just to remind you a bit about the usual quiver gauge theory story. This has been discussed a little bit during this conference, but I'll do a quick overview. The second is to overview what is this mathematical construction for these non-symmetric quivers like this. And as part of that, I'd also like to finally sort of give some evidence that this is physically meaningful. And essentially, what I mean by physically meaningful, I mean that it seems to agree with some of the properties that Hanani and his collaborators have discovered for these varieties. So, that's the plan for this talk. Are there any questions so far? I have the chat open, but I'm not very good at checking it. So please feel free to ask questions. OK, so to start, let's just recap the usual story of quiver gauge theories from sort of a mathematical point of view. So what are we going to do? We begin with a quiver Q. I use, just as a force of habit, slightly different notation than Nakajima's talks this morning, or well, today, I'd say, in that he was writing the vertices as Q0 and edges as Q1. I like to label the vertices by I. So this is my vertices. The edges I'll normally just write as arrows. So these are vertices. As I said, my handwriting is terrible with this. Vertices and edges. So here would be an example of such a thing. This is the orientation of the D4 Dinkin diagram. It's a particular choice of orientation. And then what do? We choose a bunch of vector spaces. So you can think of them as being kind of graded by the nodes of the diagram, which is to say that we have a vector space at every node labeled by V, and then we have another set of vector spaces also at every node, which we call W. And you can encode this in this nice picture here. So I've got the same underlying quiver Q at the bottom of this picture, and above it I have these kind of framing box vertices, which encode the W's. I'll often like to use this, I mean, at least a few times in this talk, I'll try to write little v for the dimension of this vector space V, and Wi for the dimension of Wi. Maybe whether it's capital or not is hard to tell from my writing, but I hope it's clear from the context what's one's been. And associated to this data, the choice of a quiver and the choice of these two vector spaces, we can form a gauge group and a matter representation. The gauge group is this product of genuine linear groups, or if you prefer, you could say it's the product of unitary groups. That would also do. That would be the compact version of the same story. But since I'm going to be using this BFN algebraic geometry approach, I want to use the reductive groups over the complex numbers. And the representation will be this big direct sum over all of the edges of the sort of bifundamental matter between the two nodes. So we have all of these V's at the bottom. They have some sort of matrix between them, and then same thing from the W's into the V's. This group naturally acts on this representation, and we're in the sort of picture, the framework for this BFN construction of the Coulomb branch. So this was overviewed in Professor Nakajima's talk this morning. I'm going to be giving a precise definition for the symmetrizable case, so I won't recap this one, but I'll just remind you it's defined as some sort of spectrum, so algebraic geometry of some ring. And that ring is a little bit complicated. It's defined using equivariant Borel-Moore homology of some space, and that space is infinite dimensional. But this works, and there's a very precise way of defining this thing, and you seem to get the right answer out of it. I'll remind you that, just a comment that actually the choice of orientation doesn't matter, because actually from a physical point of view, the matter that we should be looking at is n plus its dual. And so here, what we've really done is chosen a Lagrangian inside this larger vector space, which is G invariant. But it should not depend on that choice. Okay, so one of the kind of very interesting results of Braverman, Finkelberg, and Nakajima from a math point of view is if you start with a quiver, which is an orientation of a finite ADE Dinkin diagram, say this one that I have here, then when you apply this Coulomb branch construction, what you get out is something sort of familiar to mathematicians, or what? This is where it generalizes, but you get something called an Affan-Grassmannian slice, or a generalized Affan-Grassmannian slice. And it has the same type as the quiver you started with. So if we start with this quiver here, with whatever these data W's and V's are, we're going to get an Affan-Grassmannian, or generalized Affan-Grassmannian slice for type D4. And sort of the motto of, or one of the reasons that this construction is so exciting mathematically is, of course, it doesn't matter whether you start with a finite ADE diagram to begin with. You could start with any picture you want, any quiver, and you can sort of imagine that what you get is something like an Affan-Grassmannian slice, which a priori would be very hard to, or maybe impossible to make sense of. Okay, so I just wanted to say a few words about this, the significance of this result, and for that I need to sort of remind a little bit of notation. So what's going on here? So associated to our quiver Q, there's a certain semi-simple algebraic group, or maybe a Lie algebra if you like. And it's really not Q that's important. So for example, here, if this is our quiver Q, then all that mattered is the underlying graph. So D4 would be the appropriate type. So first, type D4, you can find a variety of algebraic groups. Strictly speaking, we want the adjoint type 1. And next, what we can do is take the data of the vector spaces W and V, and we can use them to build a pair of co-weights. So these are both co-weights for the group. So which is to say that lambda and mu are, you can think of these as homomorphisms from the multiplicative group C star to G, and more precisely into the maximal torus. And if this notation looks funny, what I meant here is these are fundamental co-weights. I mean, this maybe is not so important, but and these are simple co-roots. And there's a lot of co going on, and that's because there's some sort of Langlands duality that will tend to happen here, although in finite ADE type we will not see it. As has been discussed in Nakajima's lectures this week, this variety, this Affan-Grassmannian slice, is some sort of geometric avatar of a weight space. And he gave a precise discussion. We meant to take some sort of attracting set and take its top for a Moore homology, and we'll get sort of somehow canonically identified with this weight space here. And I should say the V lambda here is a representation of the Langlands dual, which is sort of G dual. And now we see that something like lambda, which is a co-weight for G, becomes a weight for G dual. And so this makes sense as a highest weight representation. And in finite type, this is some consequence of the geometric Satake correspondence. But in general, this is a conjecture. And again, I'll keep referring to Professor Nakajima's very nice lectures. He has been discussing exactly what is expected. So I'll sort of push this aside, but we can, again, the key word here is somehow, this is some sort of geometric incarnation of a weight space, of a representation of the Langlands dual group. But as I said, because we're dealing with something like finite ADE type, or more generally a symmetric type, Langlands duality is not really very exciting. When we switch to talking about symmetrizable types later, then we're getting, well, something slightly more interesting, perhaps. Okay, so again, this is a quick recap. Just to tie this into some of the previous lectures in this conference, I just wanted to mention, what is this space W lambda mu? Well, here I've used a lot of notation that I maybe don't entirely want to set up, but you can think of these as some sort of scattering matrices. It's a space of scattering matrices. And to just jump whatever this line here is, this is supposed to be a moduli space of monopoles, or singular kind of Dirac monopoles on R3 for the corresponding compact group. So we have G of 8E type is the corresponding compact group. This is what we're supposed to be looking at. For those of you who have watched Professor Urtubi's lectures from the first week of this conference, this may look sort of familiar. This hecatype is something about the Dirac monopole, and this Gauss decomposition factor here is telling you something about the behavior of the monopole kind of in scattering to infinity. I'm being vague because I don't know the precise link. But again, this is some expectation, physical expectation that was known before all this mathematical excitement around Coulomb branches developed, which is that the Coulomb branch should be this moduli space of singular monopoles. I think the most precise link that I know of at the moment is perhaps in the work of Bolomor, Demofte, and Gaiotto. Of the appendix to their paper, they give some explanation for how this comes up, but yeah. So, but maybe the case that is best understood is when this lambda parameter is 0, which is to say that all of these w's are 0, so there's no box vertices. Then in that case, there's another way to write this variety, namely, so that I would write w0 mu, but this is really based maps from sort of algebraic maps from, or holomorphic maps from P1 into the flag variety of this type. And they're based in that they send infinity to some fixed point, let's just say B. So they fix a particular Borel, plus the requirement that this map has a particular degree. Degree has to do with when you pull back line bundles, what are the degrees of those line bundles on P1. So anyway, so that's encoded by mu, which is to say the V's. And this is actually almost precisely what was said in one of the lectures of the first week. And this story is an older one, but probably in the form I'm using is probably due to Jarvis, among other people. I don't, off the top of my head, remember the full backstory. But so there is some actual precise link to monopoles in this particular case, but there's an expectation in general. Right, OK. It's also worth mentioning that, so I said scattering matrices, but this space is also called a generalized Aswin-Grassmannian slice. And that's because in the case when this mu is what's called dominant, so I'll write this, if mu is dominant, then W lambda mu can be embedded into the Aswin-Grassmannian for G. And it's sort of a transverse slice between two Schubert varieties. So again, this is a lot of notation, but may be familiar to some of you already. So there's Schubert varieties in this Aswin-Grassmannian, and you can look at the inclusions of them, and you can say, can I find a kind of transverse direction? So if I had a larger super variety, a smaller one, and then we have a slice, the slice is going to look like this. So this is our W lambda mu. I guess maybe I should use more colors. This would be Gur mu, and the red would be the larger guy. Okay. Okay, so to move on, I'd like to talk about symmetrizable contra matrices, because this is the required input data for our construction. So let me remind you, or introduce this notation of what a Cartan matrix, what does it mean for it to be symmetrizable? It means that you can find these integers di, positive integers, such that when you multiply by them, the Cartan matrix becomes symmetric. So you get this equation here. I think probably simplest to illustrate with an example. So if we look at type G2, where the Dinkin diagram is this orientation, I always get mixed up with what the right convention is. Should it be left arrow or right arrow? But anyway, they're isomorphic, obviously. The Cartan matrix is 2, -1, -3, 2. So I claim that the symmetrizers are 3 and 1. And again, just for sake of clarity, what does that mean? It means that if we take the matrix 3, the diagonal matrix 3, 0, 0, 1, multiply that with the Cartan matrix, we're supposed to get a symmetric matrix out. And here we get 6, -3, -3, 2, which is indeed symmetric. So type G2 is symmetrizable. Any finite type is symmetrizable, but in general, a Cartan matrix for a Kac-Moody type might not be. So we want to make this restriction that we're looking at symmetrizable things, because these numbers di, which are called symmetrizers, yeah, I guess I should say that, because these were in the title of my talk, play an important role. Okay, so what else do we need to do? Well, we somehow need to choose an orientation of what I will just loosely refer to as the underlying graph. I don't want to get into the full combinatorics. It's not really that complicated, but just to say that, for example, if we look at A2, B2, and G2, these Dinkin diagrams, they have a lot of arrows and information, but from the point of view of this construction, all that we want to know is somehow an underlying graph, which is to say just these all kind of look like this, right? And so we have an orientation either left or right. And so when we do this quiver, this construction of Q, so it could either be this going to the right or go to the left, we don't remember these extra decorations on a Dinkin diagram. So the Dinkin diagram as a graph is not kind of the important thing. That's some other thing for us. So we want to pick one of these. Pick some orientation of this underlying graph. And finally, just as in the finite type, we want to choose a pair of graded vector spaces V and W. Okay. So given all of this data, so that is to say the Cartan matrix, the choice of symmetrizers, the choice of Quiver, and these vector spaces, we can construct this variety, which we're going to refer to as a Coulomb branch. So I'll call it MC. But in fact, this construction will not depend on the choices too particularly, in the sense that you don't actually need to, you can pick whatever symmetrizers you want, and you can also choose different orientations. So for example, here, it doesn't matter which one of these we take. We're going to get the same Coulomb branch up to isomorphism. And so it's kind of meaningful to actually write a picture like this down. So this picture, this is meaningful. Meaningful is the wrong word. This is sort of well-defined. You just pick an orientation, you pick symmetrizers, and it's well-defined up to isomorphism. And by this, sorry, MC. Oh, yes.
Sorry, there's a question. Whether there's going to be a difference here between type B and C?
Oh, yeah, great question. So if it's B2, C2, then no, right? Because B2 and C2 are just relabelings of each other. Sorry, maybe it's clear, but these two things are that's going to be the same. But when we start dealing with actual like Bn versus Cn, then it does make a difference. Yeah. Maybe my wording here is a little confusing. So I don't mean to say that you can just choose any random numbers di. Rather, they have to satisfy this equation. And so when I say that it's independent of this choice, I mean to say that, for example, here, I could have taken, just to an example, we could have taken D1 is 6 and D2 equals 3. Sorry, not 3, 2. I could multiply both of them by 2. And in fact, more generally, I can get something like 3C and 2C. So, which is to say, it's well defined up to a constant multiple. And for any of the finite types, or more generally for any decomposable Cartan matrix, symmetrizable Cartan matrix, the symmetrizers are actually well defined up to some constant scalar. So in fact, you can pick one which is like a minimal one. So I've chosen it in such a way that they have no, such that they're relatively prime, right? But you can more generally put whatever number here you want. And that's where we'll see the difference between B and C, because the underlying graph for type B and C kind of look the same. They're just something like this, just a line. But if I get them, C, I think, has the big one on the end, right? I think this is type C. So here the symmetrizers will be like D1 is 1, and well, maybe I'll just write them like this. So if this is type C, and I believe the symmetrizers of 1, 1, 1, 1, 1, 2, and I think Bn I'm always embarrassed. Maybe I have these backwards, but assuming I have these Cn and Bn correct, then I think it goes 2, 2, 2, 2, 2, 1. And so the construction will see the difference. Yeah, that's a great question. Yeah, sorry if my wording was a little unclear. So, but essentially, so it's essentially a unique choice of these Ds up to a scalar. Yeah, and so here up to isomorphism. Some other comment I want to make here. Oh yes, right. Final another remark. I'll just put this here. So if all di are equal, we will recover the usual Coulomb branch, which is to say, if they're all equal, you don't need to do this new construction. Oops, my chat box is over that. If they're all equal, you don't need to do this construction. You just go back to the usual story of Quiver gauge theories, and you'll get the same answer. So for example, for type A2, there's no need to use symmetrizers. It's already symmetric. You could use them if you want, but it's not going to do anything new. OK. Yeah, so basically, it's more or less independent of the various choices, but it does depend on the Cartan type. So B and C are different, and so on. OK. And before I get to the definition, I just want to mention kind of a motivating result for us anyway was that, and this is in my joint work with Nakajima, that if we take any finite type quiver, we're going to get the same answer, this sort of scattering matrices picture. So what should be some sort of space of singular monopoles. This is a generalized slice in the Grassmannian. And I'll mention again, this is kind of repeating the same thing, but because of geometric Satake, we again get some sort of geometric avatar. So this W lambda mu is again a weight space inside some representation. But now there really is a genuine Langlands dual. The Langlands dual is, for type B will be type C, and so on. And we again hope, as is explained in Professor Nakajima's talks, that this geometric Satake should extend from finite types to all symmetrizable types.
Okay, sorry, Alex. There's another question. Are we seeing edge multiplicity per Hanani's conjecture? Or sorry, per Hanani's lecture, sorry.
That's a good question. I'm not sure. I guess let me say something and you can tell me if I'm on the right side. So another thing you might do is you might look at, say, affine. So here's another Dinka diagram. This is like affine SL2. So, and here there's actually a double edge, right? And so when we do this construction of the Quiver gauge theory, we actually need to include this edge twice. So in other words, the matter would be like maps from here to here, plus another copy of maps. Is that the sort of edge multiplicity you mean, or something else? Sorry for the boring question, but yes. I see. So this is something I was glossing over. But essentially, when I say underlying graph, that underlying graph may have multiplicities in the same way that affine, even for symmetric types, this affine SL2 has an edge multiplicity. And that has to do with the fact that the Dinka diagram here, these entries are not relatively prime. And so when you do the same construction in symmetrizable type, you should incorporate something having to do with the GCD. Namely, you want GCD many edges, roughly. So yes, yeah, I was going to gloss over that point, but that's a great question. So there is some meaning of edge multiplicity here, but I'm sort of ignoring it. Maybe another way to say it is when I say underlying graph, I'm just sweeping under the rug that it may include multiple edges. But if we're happy talking about type G2, for example, there is no multiple edge. It's simply a single edge. Yeah. So in general, as I said, it should be the GCD of these entries, many edges. Yeah. I hope that sort of clarifies a little. So I did want to mention the construction, and it's a little strange, but I wanted to briefly try to explain it. So essentially, the way to say it, there's a lot of words written here, but the way to say it is essentially that it's the usual construction of BFN construction of a Coulomb branch for Quiver gauge theory, but we use a bunch of different formal disks. So you may have seen in some of the earlier talks of this conference a lot of pictures where you have sort of a formal disk here. This is a formal disk inside the complex plane, and then we have a real direction, and we're thinking about this happening on sort of R3, which is isomorphic to C cross R. And a lot of this BFM construction is somehow stuff happening in terms of like inserting monopole operators on this line. And our construction kind of looks like this too, but somehow we're taking multiple formal disks, which are related to each other by covering maps. And so I don't know precisely the way to formulate it in terms of these pictures, but maybe it's sort of still useful to have in the back of your head. So essentially, for every node of the Dinkin diagram, we're going to take a different formal disk. And to jump ahead, what will happen is that whenever there's an edge between, say, I and J, we have a picture where we have the formal disk at the vertex I, the formal disk at the vertex J, and then we put some kind of cover between them. And this D is not, it's not independent of I and J. Maybe I should label it by IJ or something. So there's a disk here, and I want coverings of particular degrees, namely they're these. So somehow I take these symmetrizers and I divide by the GCD. And in this way, we'll get a whole bunch of formal disks, which are related to each other and kind of by these diagrams. OK, but with that said, what are we doing? So on each of these disks, we're going to take a vector bundle, and the rank is VI. So remember, the VIs are part of the Quiver data. That's the dimension of the circle vertices. And we, for every single one of them, we're going to choose a trivialization of that vector bundle. So if you take 1 and 2 together, what we're getting is a point in the product of affine Grassmannians. This is not going to fit. Product of GER GLVI. So that's maybe one way to think about this. This is just a point of the affine Grassmannian, but written in terms of vector bundles. And then what we also have is essentially for every edge in our picture, in our quiver, we have a morphism of bundles. So for every node, we have a map from a trivial bundle of rank WI. Again, that's part of the Quiver data, to our vector bundle EI. And then we have, for every node morphism in the quiver, arrow in the quiver, we have a map of vector bundles EI to EJ. Now, the problem here is that EI is naturally living on the disk DI, and EJ is naturally living on the disk DJ. And this is why I was telling you about these coverings. What we do is pull them back to some common cover, this DIJ space, and that's where we look at a morphism between them. And that's the right data. And there's a final condition, which is that if we take either of these morphisms and we apply these trivializations, so for example, let's see, we can directly apply phi to SI. So we could look at phi composed with SI, right? Because SI is a map from this trivial bundle to EI, and then phi is a map from that same bundle to another trivial bundle. But the point is, this is only defined, or a priori defined, only on the punctured disk, DI star, because this trivialization was only happening on a punctured disk. And the requirement that we want to make is that it's not, that it actually extends. So it extends to a map on the full disk. So in other words, this thing a priori might have a pole. If you kind of write it out as a series, it might have a pole. We don't want any poles. This should be regular. And similarly, you can imagine using the trivializations to trivialize EI and EJ, and there's some big diagram involved with I got trivial bundles here and here, but I have to pull back to the common disk, etc. That should also become regular, so or remain regular rather to say. And this defines a moduli space, which we call R. So it's all of this data. It should be vector bundles, trivializations, morphisms, with the condition that they remain regular after this operation. OK. And just a comment, I mentioned on the previous slide that if all of these symmetrizers are equal, then you recover the usual Coulomb branch. here we can see that it's just saying that if all of these degrees are the same, then you can effectively kind of forget about all these different disks because they're all having covering maps of the same degrees. And you can replace them all with, I guess, the source of that. And then you'll just recover the moduli space R that was discussed in Nakajima's lectures. OK, so it looks a little bit of a mess, perhaps, or maybe not. But this does seem to produce the correct result. OK. And just a little bit more. So this space has a natural action of a group, which is the automorphism group of the trivial bundle, because that acts on these trivializations here. So if we take the trivial bundle of rank VI, you can act by automorphisms. And in here, I haven't put punctured, just full disk. So, OK. So now we have an analog of this theorem of Brodmann, Finkelberg, and Nakajima that there's a way to define a ring operation on this equivariant Borel-Moore homology such that it becomes a commutative algebra. And again, there's this, just to go back to these formal disk pictures, if you imagine the same picture, somehow this is supposed to be convolution, which is supposed to be insertion of monopoles, that you're sort of inserting them on this line and convolving them to produce a new operator, composing them somehow. Except for that, again, these are happening on perhaps separate disks. And so it's a little, I'm not sure what picture to put, but this is kind of an intuition. There's some convolution operation happening here. But we don't use the same proof as the ordinary case because we don't have quite the same picture. So rather, we prove this theorem by just embedding this algebra into a commutative ring. And finally, armed with this theorem, sort of theorem definition, to define the Coulomb branch, you have a commutative algebra right here. It makes sense to take its spectrum. And that will be the definition of the Coulomb branch for us. Any questions? OK. Then I'd like to talk about some of the properties of this construction for the remainder of this talk, essentially, and then a couple examples to end. So the first is sort of an algebraic geometry statement. It says that this is an irreducible normal affine variety over the complex numbers. So, which is basically to say that it's nice. It may be singular, I should say. This space could have a lot of singularities. It might look like a cone, something like that. The sort of spaces that, for example, Hanani has been discussing in his lectures, or was, excuse me. But it's still fairly nice. It's normal. And we can also compute dimension. It's not sure what happened here. The dimension of this space is just twice the sum of these VI circled nodes. That's a dimension over the complex numbers. So in Hanani's lectures, he was often talking about quaternionic dimension, where we just divide this by 2. OK. Another thing we can do is, I guess in physics terminology, kind of consider an omega background, something like this, where what mathematically means we turn on an extra equivariance here. So instead of considering just G of O equivariance, we allow a loop rotation. And here you have to be a little careful. This is actually where the choice of symmetrizers plays a part, because the action on the different disks will be slightly different. So here, maybe I can say it this way. We act on the disk DI. Remember on DI, or maybe don't remember, but here there's a coordinate Z. So this is like the spectrum of some ring with coordinate ZI. And ZI should go to, if S is an element of C star, it will take ZI to S to the DI ZI. Whoops. And you can, sorry. So, which is to say, the loop rotations on the different disks are at different degrees, different weights. But what matters when I say something like that is that when you check this diagram here, you can see that all the C star actions are compatible with each other. So there's some single C star action up on the top, which it's compatible with this picture. It's all equivariant. Okay, so anyway, you turn such a thing on, you'll get a non-commutative ring now, but it is a deformation quantization of the coordinate ring. And maybe the upshot of this is that it tells us that this Coulomb wrench has a Poisson structure, a sort of holomorphic Poisson structure. And in fact, you can show a little bit more that if you, we mentioned that the Coulomb wrench is singular, but if you look just at the smooth locus, it will in fact be a symplectic variety. And here I should say holomorphic symplectic. Everything is over the complex numbers. And Professor Nakajima alluded to this. There's the expectation that these varieties should be hyperkähler, maybe from a physical perspective. We don't know how to do that here, but we see some remnant of it, which is that these are algebraic varieties over complex numbers, so maybe Kähler, but they're actually more than that. They have a algebraic holomorphic symplectic form. So it's supposed to be some remnant of a hyperkähler structure. Okay. So these are both kind of mathematical properties, but oh, sorry, maybe one more. I guess this is also mathematical, but getting into the ones that are maybe slightly more physically motivated. So it's worth saying that there's some sort of birational map. So it's not an isomorphism. It's not actually a map. It's a map from an open subset here to one here. And on the right side, what we've got is a cotangent bundle of C star to some power, and you have to mod up by some group. This is some very simple space, but it's worth mentioning that each of these factors that we're seeing is just a R3 cross S1, because the cotangent bundle of C star is just C cross C star, which looks like R squared cross R cross S1. And this is meant to be reminiscent of the sort of usual classical, or I think classical picture of Coulomb branches without quantum corrections. You normally get some calculation which looks like this. And so what we're thinking is that this Coulomb branch that we've defined is somehow the quantum corrected thing, object. And so, and here we do get such a map. So they are actually related to each other. Most points, sort of generically, it looks like this space. These SVIs are some symmetric group, but maybe you can ignore this. It's basically a big product of S1s and copies of R. Okay. Okay, maybe the more significant thing is that this funny definition that we've given satisfies the twisted monopole formula, which is something defined by some collaborators of Haneni and himself. And I won't write down the full combinatorics, but it's a modification of the usual monopole formula, which somehow involves the Cartan matrix. And so this is probably the biggest evidence that what we've defined is matching with the physical intuition. There's some sort of this formula that is equal to the graded dimension of this ring. You have to be a little careful in that, of course, it's possible that this doesn't converge, this thing on the right side, whatever it is. It might not actually converge as a Laurent series. So there you need some extra conditions like being good or ugly. In fact, it's possible to say that this left side, this ring, has a filtration. So you can filter by bigger and bigger pieces. And each of those pieces actually has its own monopole formula, and those ones do make sense. So even in that slightly weaker sense, it is true, but we have this formula. Okay. And I wanted to recall, since Matthew Bullenmore's talks in the first week of this conference, there was a discussion about sort of flavor symmetries of 3D n equals to 4 theories. Again, what I'm talking about here is maybe not a 3D n equals to 4 theory, I'm not sure, but it certainly has some of the same symmetries you would expect. So there was one thing that's been discussed as a sort of topological symmetry, and that comes from the pi1, the fundamental group of the gauge group. In this case, that's going to just be, these are a bunch of general linear groups, so we'll get a bunch of copies of C star. And you could just say it's to the number of nodes, but maybe some of these V's are zeros. Anyway, it's not, it's just, n is just however many nodes have non-trivial V's. And so for free, this group will act on the Coulomb branch. but it's also possible that it will extend to a larger group. And one way that happens are these balanced nodes of the quiver. So here's a picture for type G2 quiver, and this one is balanced. It's completely balanced, in fact. So the sort of I don't know, I forget the word. Oh, I see this is a question. Well, sorry, let me finish that thought. So, and I'll turn back to the question. But here, there's actually every node is balanced, and so there's actually a full G2 symmetry on this Coulomb branch. And in fact, I believe that this Coulomb branch is like a minimal nilpotent orbit for type G2 or something. I may have that wrong. So this is I think it's a nilpotent orbit. But as Panani had discussed in his lectures, if you look at them, sometimes you may even get a bigger symmetry group than that, but you can definitely get something from balancing. The balancing, when I say balanced, you need to take into account the Cartan matrix. So effectively, what this means is that, in this case anyway, mu is 0. A balanced node, in my notation, would mean that the co-weight has component 0 somehow. Okay. Sorry, so I saw there's a question. So the convergence question, oh yes, so about the twisted monopole formula. Yes, so convergence, I believe that being good translates into, I think, mu being dominant. Again, sorry, let me just remind the notation. The Coulomb branch is this Aswin slice or generalized slice lambda and mu. I think that good is mu is dominant and bad is, I might have this wrong for non-symmetric type, but I think it means that mu paired with alpha I is greater or equal to -1 for all I, something funny like that. People call this almost dominant. The claim is that for almost dominant slices, there is a conical action, or no, sorry, convergent action, and dominant corresponds to being conical, I think. I might have that wrong. Yeah, so it's a great question. When does it converge? There is a good and bad condition and then ugly, and they do mean something in terms of the representation theory of that Cartan matrix, or in terms of the data of that Cartan matrix. Precisely, I can't remember, but it's something like this. Again, I'm thinking of the symmetric type. Maybe this -1 should be something else if it's not symmetric, but maybe I'm mistaken. Okay. Oh, and finally, I'll just mention that there are also sort of Higgs flavor symmetries, which look a lot or effectively equivalent to the ordinary quiver gauge theories. So I'm copying here the notation from Nakajima's talk earlier today, is that we have all our framings, these W's. What we take is the maximal torus inside the general linear group of that W. So T of Wi inside GL is a maximal torus. For example, the diagonal matrices. So we have flavor symmetries coming from all of those. And we also have some flavor symmetries potentially coming from the homology of the graph. So here I've written this as the Betty number of the underlying graph, Q, this quiver. Perhaps we have those. So if we have a circle, for example, or any sort of loops, we'll start to see extra flavor symmetries coming. But in any case, using this, just as with ordinary Coulomb branches, there's some way to turn on masses and produce parcel resolutions. Those would be integral sort of parameters. And there's also ways to deform the Coulomb branch using the same, but using also this sort of mass parameters that I maybe won't get into. But essentially, the motto is most of the same structures that appear for ordinary quiver gauge theories extend to this definition, and they behave in the exact same way that you would expect. So there is a monopole formula. There is several notions of symmetry, and there are these mass parameters, etc. Okay, so that's a lot of sort of technical things. I wanted to mention an example which has, I think was touched on in Professor Hanani's lectures. So these are some particular singularities studied by these collaborators of Hanani. in several of their papers. They denote them by H lower D K. And what we're looking at here is sort of D vertices. And with this extra condition at the end, we might have a bunch of, well, the Cartan matrix might have this sort of structure where we have K edges. So in terms of Cartan matrix terms, the Cartan would look something like 2, 2, 2, and we're supposed to have a bigger guy here. So I believe it goes like, maybe let me not try to do it on live. But you want to arrange it in such a way that you have a long node here. So, okay, and what they claim is that what they expected or checked themselves is that with their sort of physical definition of what the Coulomb branch is, that it should be this particular quotient here. They would write this as the quaternions to the power D mod a cyclic group, but I've written it as the complex numbers twice to kind of highlight that this space has a symplectic form because it looks like C to the D plus another copy of C to the D. And so I just wanted to, there's this example that you can check using our definition, indeed, that this also is true. So as expected. So we verify using our definition. And I should add that what does this mean? It means that this group here is a cyclic group of order K, and it's going to act on the sort of, I'll say it this way. By this, I mean Z mod KZ. And this acts on C to the D plus C to the D. And here it acts with weight 1, and here it acts with weight -1. And I find this to be a very interesting example. Another thing you can see here, which I'm sure is how these people were thinking about it as well, is that this also, it respects natural GLD actions. So from the point of view of this, sorry, I'll just erase this. When I write this isomorphism, I mean, we're using our definition to check this. But so on the right-hand side, there's a natural action of GLD, which just acts on one of the C to the Ds. So I'm thinking of this as C to the D plus another copy. So I'm acting on one in the natural way, and on the other one in a sort of, in a way to make this a symplectic action. So, and there's the residual action of this group on this quotient. And on the other hand, from the Quiver point of view, we have a bunch of balanced nodes. In fact, all of these nodes here are balanced. And that tells us that at least there's like an action of SL. So there are D-1 vertices. That's a Venn diagram of type A D-1. So we'll get a SLD action. And in fact, this SLD action extends to a GLD action, which is precisely the one that we're getting from this quotient picture. So it's kind of a nice story here. This is an example that I like in part because it is not a finite type quiver, right? You can take D and K to be whatever you want. And thanks to the work of these fine people, we know what the quotient is. And more than that, this is an example of a minimal singularity in that there aren't, there's basically only two symplectic leaves of this quotient. There's sort of a big open piece, and then there's the origin. There are nothing in between. The Hasse diagram is basically trivial. There's just, it is singular, but there's nothing interesting going on. Okay, so yeah, so this is another sanity check that our definition seems to work because it matches this prediction. And just a sort of comment, which is one thing that this tells us, which is maybe interesting to mathematicians, is if you write down these two quivers, then from what I just said, what we're supposed to see, I know I wrote this one backwards, but because my type G, by convention, I put the big one on the left. Anyway, these guys look like C2 mod a cyclic group Z2 or a C2 mod Z3. But on the other hand, when I say equals here, I mean the Coulomb branch of this thing is isomorphic to this, and the Coulomb branch of this. Sorry, I would not be very precise. On the other hand, I was telling you earlier that the Coulomb branch of a type C2 quiver is an affine Grassmannian slice of type C2. And using my notation, it looks like this. It's the first fundamental coweight, and that's lambda, and mu is equal to 0. And similarly, if you take this type G2, what you're going to get is the lambda is the second fundamental, and mu is the first fundamental. That's an affine Grassmannian slice inside G2. And I don't know. I had never heard that those are quotient singularities. In fact, I've told several people this, and they seem surprised. But based on this physical prediction, this is what we get. So it's kind of a nice fact. So it tells us something new about affine Grassmannians, surprisingly enough. And I'll mention that, in fact, these two examples here of affine Grassmannian slices have appeared in the work of Malkin, Ostrich, and Dvorak, because these are examples of minimal degenerations, just as this is a minimal degeneration. In other words, again, the Hasse diagram is only two things. It's sort of the whole and a point. That's the Hasse diagram. There's an open, smooth part, and there's a point, which is the singular point. And so these have been studied before by these people, as well as, for example, Daniel Juteau and some others. These are interesting affine Grassmannian slices, and we learn from this that, in fact, they're just quotient singularities. OK. So yeah, I really like this story, and I'm very grateful for these, the work of these people that are pointing this out. OK, and so in the final couple minutes, this is all sort of speculative because I don't know anything to say here. It's basically the model, but there's a question which I've talked about Coulomb branches for quivers. What is the Higgs branch, or even is there a Higgs branch? So question mark. There may not be such a thing. I don't know, but by analogy with the usual quiver gauge theories, I would, it's natural to propose that the Higgs branch for such a thing would be sort of a Nakajima quiver variety. Here would be a Nakajima quiver variety, sort of type F4, whatever that is meant to mean. So I don't know what that means, but I just wanted to mention, I think I should mention that people studying representations of quivers and mathematically have actually come up with several ways of dealing with non-symmetric types, for example, type F4. And two of the kind of main contenders, I would say, are the theory of modulated graphs, which goes back to Dlab and Ringel. There's also an interesting paper of Tingley and Nandakumar on this topic. And then there's also more recent work of Geisel, Clark, and Schroer. And I also wanted to add that, so I don't know how this is related to this Higgs branch or even the Coulomb branch, but these two works here kind of inspired our construction. So I think I should acknowledge that sort of there's some link, at least a link which is hard to make precise, but somehow this motivates the definition that I gave. Right, but I don't know of any actual notion of a Higgs branch here. And I thought I would end then on that topic by just sort of reproducing a diagram from Hanani's lectures, which is the following picture. It's sort of a large, it's a Venn diagram, right? So there's symplectic singularities, there's Coulomb branches, there are hyperkähler quotients, which I guess you could say are, at least from a mathematical point of view, would be sort of the Higgs branches. And then there's sort of all the places that they overlap or don't overlap. And sort of 3D mirror symmetry, maybe it happens here because you can kind of start to swap back and forth between the two pictures. I don't know where on this picture the non-symmetric ones live. So where do these ones for symmetrizable types live? So they might be out here. Maybe they don't even have symplectic singularities, or maybe there are symplectic singularities, but not hyperkähler quotients, or et cetera. So I think this is an instructive way of thinking about it. They could be somehow anywhere, but we don't know at the moment. I think this is a very interesting question. So I see I'm getting close to the end of the time, so I think I'll just stop here then. And thank you all for listening.
All right. Thank you very much for the talk. Are there any questions? Yeah, there's a question from Aswin Balasubramanian. Okay.
Hi, Alex. Yeah. Thank you for the great talk. So Yeah, my question is actually about the last figure you drew. So, I mean, I think when physicists talk about Coulomb branches, they probably already sort of assume that it's a symplectic singularity. So I would like to know, like, what is the thing that, like, mathematically, if you take the BFN definition or something, what is the thing that you need to check there?
Yeah, that's a good point. I guess it has to do with what does symplectic singularity mean to you precisely. I meant, for me, I'm thinking in the sense of Beauville. Or I should put the R the other way. Maybe that's not what Professor Hanani meant. I'm not sure. So for me, in the sense of Beauville, and what that entails here is that for any of these Coulomb branches, so sorry, I have all my Zoom tabs over top of where I wanted to write. But if we take one of these varieties, if I can get this to open, sorry. Okay, there we go. We want to choose a resolution of singularities. So it's a smooth variety with a proper birational map onto this Coulomb branch. And what we need to check, and maybe I'll call that pi. What you need to check is that, so I talked about how on this Coulomb branch has a Poisson structure, and actually it's a symplectic, a holomorphic symplectic on the smooth locus of the Coulomb branch. And what you need to check is that when you pull back the symplectic form from the regular locus, a priori, again, that's an open subset of here, and so when you pull back, you're getting a two form on some locus inside this resolution. You need to check that this actually extends to a regular form. That's what it means. Sorry. It's a technical thing. So it's somehow, this means that they're nicely behaved.
And this resolution is, you're not assuming it's a symplectic resolution because that may not exist.
No, it just means any resolution, actually. Yeah, that's right. So there may not be a symplectic resolution. That would be the ideal thing. You just choose any resolution of singularities, pull back the symplectic form on the smooth part, and check that it actually has no poles. It actually extends to the whole variety. It may seem like a kind of technical condition, but it has a few nice consequences. So one of them is that this implies that, for example, the Coulomb branch has finitely many symplectic leaves. It implies several other things. The singularities are all Gorenstein. I forget exactly. There's a very nice theory of these symplectic singularities. So somehow mathematically, it seems to be a reasonable condition. But actually checking that it's true, you need to do a little bit of work. So in fact, so for ordinary quivers, you can see that you can prove that they have symplectic singularities, the Coulomb branch for usual quiver gauge theory. This is something I was able to prove, but I don't know how to prove it for symmetrizable types. So.
Okay. I mean, yeah, I was also confused in Hanani's talk because at least the naive thing that I had in mind from a physicist motivation would have meant Coulomb branches sit inside symplectic singularities. I mean, maybe if you include the conical conditions, some ones are out and those are the ones you want to call bad or something, but modulo that, I would have put this inside the bigger circle.
I see. Yeah. For me, it might lie inside or it might not. And you can have symplectic singularities and not be conical, and vice versa, of course. But
no, that's fine. So
they're all okay.
Definitely, yeah. That's definitely an issue.
I guess I can add one thing is that just to expand slightly, if you're taking any finite type, even symmetrizable, so like B, C, F, and G, those always are symplectic singularities. And from, as you asked before, we know when they're conical. So those ones are pretty well behaved in terms of where they fit in this picture.
I have another question, but I'll maybe wait to see if somebody else has a question before I can.
I saw in the chat that maybe there's one. I'm sorry if I haven't, I didn't address earlier.
It was
or maybe that was old.
Comment. Yeah. Are there any further questions? Okay, well, you can go ahead, Aswin, I guess.
Yeah, maybe I'll ask my question. So I got a message. I wasn't sure. Yeah, okay. So my question is about this notion of minimal singularity, the ones that have just two leaves. So from the Quiver, I mean, my general sense from Hanani's talk was that if there are sort of a lot of ones, that's already a sign that that's something minimal. There's sort of nothing to subtract further. Is there a simple algorithm that tells you, like, just by looking at the Quiver, whether you have something minimal?
Not that I know of. I guess, and in fact, I don't know the right statement. I think that if you're a finite type Quiver, then you can say something. The issue is when you leave finite type, there are some strange things that can happen. And it's possible that that has to do with affine types and not things beyond that. So maybe let me give an example though. And I hope I get this right. So this is just an ordinary Coulomb branch, but for affine type, for affine SL2, this is a Coulomb branch with no framing at all. And here, I mean, there are ways of reducing this, I guess. So, but let me say, I think, I feel like I'm going to get this backwards. This has some strata that you might not expect, is what I mean to say. Sorry, let me try to be, maybe I think I can think of it this one. So I don't know, I guess a very naive guess is that the Coulomb branch for this would be smooth, but in fact, that's not the case. And there are more strata. I'm not sure if perhaps Professor Nakajima will be talking about this in his lectures, but here this contains pieces which look like, hopefully I can get this right, smaller Coulomb branches where I take like K or something, where K is less than D, and I take the smooth part. But then you have to multiply by some symmetric power of C2, I think. And hopefully I get the numbers here right. D minus K, C2. And so I don't know, something strange is happening that from this Quiver, I don't know why you see these symmetric powers, for example. And in particular, this piece here actually has further decomposition into leaves that, anyway, so I think that for general Quivers, I personally do not know what the right answer to thinking about these combinatorics is. I hope there is a good one, but at the moment I don't see it. So maybe this is because this is an affine type A that there's a problem, and maybe, for example, here, what you said is correct, that somehow the fact that there's a one kind of tells us that there's not much you can do to kind of do a Quiver subtraction, if you will. But in general, I actually don't know what the right answer is. So maybe it's a semi-answer to your question.
Thank you.
I think to be more precise here, by the way, sorry, I should say this is like a disjoint union, I think, from, maybe it's from 0, something like that.
Okay, are there any further questions? Okay, if not, let's thank Alex again, and I believe this is it for this session.
Thank you for listening.